So hey everyone, welcome back to my channel. I am Mihran from Mihran's Orbit. Uh, uh, so last time we talked about Hawking radiation, right? That was very interesting. I'm not sure if most of you guys heard about that, but I think most of you actually saw that. Uh, uh so so today we're going to be talking about something called cosmic rays. Uh, 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 we are going to be eventually going from space to other topics in this series. Just wait a minute. It's gonna take a little time. I think it's gonna last for like 3 months or something. No, let's just talk about cosmic rays. Last time, now this is gonna be important. We talked about Hawking radiation, which, in short, watch that video in case you need more in-depth info and also some facts on black holes. Watch that video. It's just my last video. Go to your videos feed and under this video, that will be it. But now let's talk about oh yeah, I gotta. So Hawking radiation is just like radiation coming off black holes from their perimeter and everywhere else, and that radiation eventually, hey, welcome back my experiment. That radiation eventually wipes out anything, right? So that's what's Hawking radiation in short. There's more info, I'll do that later. But cosmic rays, um sounds familiar for those of you guys, some of you guys. I don't know if you have seen that video, but okay. Uh so so cosmic rays were essentially rays that weren't even possible. For humanity, they didn't think that that would have been possible, but it was because of the black holes and neutron stars. Last time, neutron stars put a little effect into our videos, but now it's going to be very important because that's what's 90% of the video, so make sure for that. But in short, cosmic rays are just rays coming from outer space, just like expected. It's cosmic rays. It's just like expected, so it's cosmic rays, and it comes from the outer universe near, everywhere else in the universe. It comes from stars, black holes, neutron stars. And speaking of that, neutron stars, neutron stars are the neutron stars are just very very condensed stars. Now, last time I didn't explain a lot of neutron stars because it wasn't really the main focus of the video. But now let's talk about neutron stars. So neutron stars are just these very condensed stars which happen after a hypernova, not a supernova. Hypernova, after a very condensed star explodes, which is how I put it. It's not really exploding, okay? Some of you guys might have got triggered on that area. It's not really exploding. It's just taking the mass right through here, and it just expands up till the gravity takes it over. That's about it. But that turns into a neutron stars, which is one spoon of neutron star is 5 times the mass of our sun. And just imagine how much cosmic rays they can do. They have so much gamma radiation in them. That's topic for the next part of our series. We aren't touching any of gamma radiation for now. Next part of the series, that's about gamma radiation, okay? So let's talk about for now cosmic rays. Cosmic rays are literally the only sources of radioactive things, and radioactive atoms are those that end up on the air. Now, there was a really cool story that I won't be able to talk about because I kind of forgot about that, but somebody who's a scientist actually got up and tried to check and measure all of the radiation using one of those what are those called? I think those are called something, but I forgot. But basically, like, the charges actually come in and they just like charge up, and we can notice that those things, and those are actually the radiation. Since radiation goes in with protons and electrons, it charges that up just enough to do this, like do this. So that's how they measured. But suddenly the radiation got up, because it wasn't supposed to, because like all of the radiation would have been in rocks and other things at the surface. When they were checking, they had a little high, but then it got so high because of cosmic rays that actually go through the ozone layer, take up so much, like take so much radiation to our surface, but most of them don't get to the surface itself, like where we are living at. So don't worry too much about cosmic rays. They won't come to your house or anywhere. Really they won't like come to any of part of your house. So like, other than that, I think, well, we have to talk about the sources of cosmic rays, because first, this is very important for us. These are the three main sources. I wish I had a board right now. Anyways, so these are the three main things. First, editor, put the graph right here. 1 minute. Yeah, put a graph right there about neutron stars, black holes, and neutron stars, black hole, and like then these are all of the things like that emit radiation. Also, another big source of radiation, a big source of radiation that is very interesting, and and you would learn a lot on this radiation topic in this series, because let's say I have some theories for you that makes a lot of sense. Like, those are generally proven by some things. So make sure to watch that. Like, the support on the last time was so much, but like, yeah. So those are all the three sources of energy, which actually give us, like, actually not the three sources, two sources, because like, yeah, there are only two sources. The third source is a mystery source. Just go right now. Not now, but the first neutron star. So what is a neutron stars? Well, let's imagine my finger is a neutron star right now. So there are neutron stars, and by that I mean like neutron stars, like pulsars, because like pulsars are also neutron stars, but they actually emit 600 flashes of gamma radiation per second. That's a lot. Now they turn into cosmic rays because they are too weak and they reach the surface of Earth. Then, so they count as cosmic rays. But then there is black holes, which create less emission, which is like making sense. It's like accurate on the name. It's black hole, and the other one is neutron star. There are some cool things happening inside the neutron star. Wait for that video. And also, changing world is coming again. But other than that, neutron stars like are actually blinking so fast that they give gamma radiation as well as black holes. They create so much of these rays of light coming down to Earth. Just imagine this is Earth and these are the cosmic rays. These rays are called cosmic rays. These are called cosmic rays, right? So these cosmic rays are like so energized, but not really energized too much, because, well, they don't burn everything like meteors. But other than that, well, the cosmic rays topic is kinda done. So let's talk about the mystery sources now. Basically the 5% of the other video, as well as neutron stars. But like the thing about these two mystery sources are these making sense also. First, stars. Now you would normally not expect a lot of gamma radiation from stars. So that's why, like, some people might say, yeah, it's obvious that cosmic rays come from the sun and the other things, but it's not really obvious when you think about it a little deeper, because there's they can emit so low amounts of light. They must not be able to emit so much amount of gamma radiation, right? That's just logical, because like though they have so much less energy and capacity to go up and make like energy rays everywhere, because they don't have enough light alone. Like that doesn't make any sense. But if you have watched my last topic, go check it out. You know that stars have fusion happening inside them, basically when they are just trying to balance out the gravity by fusioning their atoms together, like hydrogen and helium and lithium. They merge those together and create beryllium and so on, boron, and then like carbon, all of those materials. They create those. But oh yeah, I forgot that. But the thing is these energy is actually what's powering the cosmic rays, which makes sense because like they this makes sense because like the inner core never goes down to light a lot. Like all of the light that's coming from everywhere is just coming from the outside part, but the radiation is coming from the core where the fusion happens. So that makes much more sense now that it's settled. Now the second part, which is much more interesting, although kind of weird too. Galaxy. But you might be asking, well, it's a little bit weird because like galaxies have the neutron stars and the black holes, so they emit that, right? And by that I don't mean just galaxies with those things in them. I mean not even stars. I mean like the planets themselves. They do a little gamma radiation, even though, because like all of the surface light is sometimes a little amount of them come together and become this. But when you have such a big galaxy like the Milky Way, they will put out a lot of radiation because all of those are stacked up and up and up. And not to mention the different scales, because neutron star is here and here, let's say Earth, and this is neutron star, not to scale by the way, but like this will make a little less radiation than this, obviously a little less radiation coming out from the galaxy. And that is like the whole essentially how like it work, how the cosmic rays work. And last time, well, I need to talk about some facts too. Now, there's not really a lot of facts about cosmic rays, but cosmic rays, I'll talk about a little more about neutron stars. There's actually something called neutron matter inside neutron stars, which is actually creating neutron pasta. That's right. Do you want to eat it with some sauce, neutron sauce? Well, don't eat it, because it's this kind of matter which is like it's so weird. I cannot talk it up. Like I'll say it's weirder, even though that dark matter, it's weirder than dark matter, which doesn't even exist. In case you do know what dark matter is, it doesn't even exist. So dark matter is like, how is it not stranger? How is it stranger than dark matter? Because it does not even have the existent proof that it exists. So that's weird. But I guess it actually is like that. And second fact, there are actually neutron star called Black Widow. I think, at least. No, it's not. Yeah, it is. It's taking its neighboring brown dwarf and it's feeding it to itself, like a real Black Widow spider would. Like I said, there are neutron stars which go up to 60,000 flashes of gamma radiation per second. But like there are like 3 million miles away, so we don't need to worry about those. But also, let's go to a little more facts about black holes, because last time, well, we didn't cover too many facts about black holes. So you know about black holes and wormholes, right? Wormholes have two ends, one white hole, one a black hole. You probably saw it right here when I was just talking, and it just appeared right there. But like, okay, but so essentially, these black holes can actually make another nova. Not really, but like there are two different forms of alternating the nova, because like there's no way you are gonna create so much things. So there are, you can technically make like 50 Jupiters together, actually 100,000 Jupiters together. Why am I outscaling myself? To make a sun, and that's just a sun, not even a little bigger, just a sun. So that's how much time it takes to make a sun using Jupiters. But how to create a black hole using more and more suns? It depends on the mass. But let's just assume it's the biggest planet, because like it's making much more sense if it happens. If it, not actually the biggest planet, that will make it a little uninteresting. Now let's go for three different scales: small, medium, and large. The larger planets, larger sun will actually have to only have one more of those suns to create, like the larger stars will just create, if you merge two of them together, they'll just create a black hole. Medium stars will take 10 of them, depending on the scale, but it's only 10 of them for the average medium star. Then the average small star, like the sun, like the yellow dwarfs, those actually form like this explosion, which will take like I think it might take like 100,000 something suns. But black holes can also form together to create bigger black holes, because there's nothing after black holes necessarily. But there's also neutron stars that can form together and make a bigger pulsar. Eventually they become a black hole like the other ones. And that's about it. Bye. See you next time.